In an industrial setting, a hydrocarbon fire can double in volume every few seconds. Once ignition occurs, the physical window to suppress the flames before they compromise structural steel or trap human occupants is brutally short. For decades, the engineering solution to this threat was a class of chemicals known as halons, specifically Halon 1301 and 1211. They vaporized cleanly, left no residue, completely ignored live electrical currents, and required very little storage space. But Halon contained bromine, a chemical that severely damages the ozone layer. Under the Montreal Protocol, developed nations agreed to phase out these suppressants entirely, making their production and general use illegal. Removing halon from the global supply chain created a severe engineering bottleneck. Fire protection systems rely on strict volumetric formulas, and there was no chemical in existence that could drop directly into old halon hardware and perform identically.
Protecting high-risk infrastructure now requires a complex balancing act. Engineers have to weigh the exact physical chemistry of a fire against stringent international environmental laws. The environmental ban is not absolute. The Montreal Protocol contains specific critical use exemptions for environments where current halon alternatives are too heavy or demand too much physical space to operate safely. In aerospace applications, every extra kilogram of fire suppression hardware burns expensive aviation fuel. Halon 1301 remains legally permitted in aircraft crew compartments and inside densely packed engine nacelles. Similar exemptions apply to military land vehicles and naval vessels. Personnel in these machines share highly confined, armored spaces with massive engines and volatile fuel lines, requiring the absolute fastest suppression with the lowest possible hardware footprint. Heavy infrastructure projects like the Channel Tunnel also retain exemptions. The sheer volume of the underground installations and their associated rolling stock makes dispersing alternative agents highly problematic. These legal loopholes point to a harsh reality in applied physics. When physical space and total system weight cannot be compromised, we do not currently possess a clean chemical that can match halon. Outside of those specific exemptions, the industry has turned to several distinct families of replacements. The first are inert gases, which include nitrogen blends like IG-100 and argon mixtures like IG-55. Unlike older chemicals, inert gases do not actively break the chemical chain reaction of a fire. Instead, they operate entirely on physical principles, manipulating specific heat capacity and aggressively displacing oxygen. This table details the standard thermodynamic properties of argon gas. Notice the standard molar enthalpy of formation is exactly 0. It does not react. And with a molar heat capacity of 20.8 joules per mole Kelvin, it effectively absorbs ambient heat energy. By flooding a room with these gases, you push the ambient oxygen concentration from a normal 21% down to a range between 10 and 14%. This creates an incredibly tight physiological margin. At 14% oxygen, most liquid and solid fuels can no longer sustain combustion. However, a healthy human can still breathe and successfully evacuate the space for a short duration. By artificially altering the baseline atmospheric energy balance of the entire room, the fire simply starves. Because inert gases do not chemically interact with the flames, they lack the efficiency of halon. To suppress a fire safely, you need a massive amount of gas. System designs require inert gases to reach a concentration of 35 to 50% of the room's total volume, and they must achieve that density in under 2 minutes. You cannot easily liquefy inert gases to save space. Facilities must rely on heavy, pressurized steel cylinders connected through extensive manifolds. The sheer mass of this hardware removes inert gases from consideration in weight-sensitive aerospace applications, restricting them primarily to terrestrial server rooms, archives, and switchgear housing. Achieving a zero-impact environmental footprint requires dedicating a massive amount of physical real estate to heavy plumbing.
The second major alternative category is halocarbon gases, specifically hydrofluorocarbons and perfluorocarbons. Halocarbons solve the hardware problem. They can be stored as liquefied compressed gases, allowing them to utilize lightweight cylinders very similar to the old halon systems. While they do not deplete the ozone layer, they introduce a separate, massive environmental penalty. Many of these fluorinated chemicals are incredibly powerful, long-lived greenhouse gases restricted by the Kyoto Protocol. This chart plots the global warming potential of various suppressants on the vertical axis, relative to carbon dioxide. The horizontal axis tracks their atmospheric lifetime in years. Look at the data point for Fe13, a common hydrofluorocarbon. It carries a global warming potential 11,700 times greater than CO2, and it will remain in the atmosphere for 264 years. Even agents like FM200, which have shorter lifespans, still carry a warming potential of 2,900. Because of these climate metrics, European regulations demand aggressive and legally binding leakage checks. Facilities utilizing large halocarbon systems must undergo documented, certified pressure inspections as frequently as every 3 months. There is also a distinct physiological risk. When a halocarbon hits the extreme heat of a fire, it thermally decomposes, producing significant quantities of toxic and highly corrosive hydrogen fluoride gas. Selecting a halocarbon agent allows an engineer to save physical space, but that efficiency is paid for through strict regulatory compliance and the introduction of secondary chemical hazards. Without a universal, chemically identical replacement for halon, engineers must map the specific physical properties of each agent against the unique hazards of a given room. For instance, in an unmanned aerospace engine bay, human inhalation toxicity is irrelevant. In those specific dry bays, engineers can utilize highly compact inert gas generators or fine solid particulates to save weight. But those solids would destroy the exposed cabling and delicate components of a live data center. For these manned, electrically sensitive spaces, engineers can deploy fine water mist systems. By using highly pressurized nozzles running at up to 200 bar, they atomize water into droplets as small as 10 microns in diameter. The physics of the mist drastically alters the properties of the water. It uses up to 100 times less volume than a traditional sprinkler, and because it is an aerosol rather than a continuous solid stream, the mist will not conduct live electrical currents. But there is a collateral limitation. The mist behaves like a dense gas in the open room, but it lacks the vaporizing permeation of a true gas. It cannot penetrate deep inside shielded server cabinets to catch hidden fires. Because no single system is perfect, modern fire protection requires synthesizing multiple physical mechanisms into a single facility. This cross-section illustrates the dual system design used in high-value server rooms. A water sprinkler network is installed in the ceiling to protect the primary structural space, while an independent inert gas system is piped directly into the floor void. The overhead sprinklers use a pre-action configuration. The pipes remain entirely dry until 2 or more separate smoke detectors trigger. This redundancy ensures that a single damaged sprinkler head will not accidentally flood the electronics. Simultaneously, the inert gas system is calibrated specifically for the floor void. The gas can easily penetrate the densely packed shielded cable trays where water mist could never reach, and the smaller volumetric area requires far fewer heavy storage cylinders.
To maintain legal compliance, this exactingly tuned architecture requires relentless statutory maintenance, including physical room integrity testing, to verify that the structure itself can retain the required gas pressures. The elimination of halons permanently closed the era of single chemical fire suppression. Protecting critical infrastructure now forces engineers to master thermodynamic properties, balancing the raw physical mechanisms required to save human lives against the stringent metrics designed to protect the planet.